So very good afternoon to everyone. My name is Janani Tyagarajan, and I'm very happy to be the host for the fourth session of Sharing the Learning webinar, brought to you by Spinco in celebration of the monumental 25,000 Shimadzu HPLC installations in India. Spinco is one of the leading bioanalytical solution providers in the country, bringing technology and enabling science over the last 4 decades. The purpose of sharing the learning is to impart analytical knowledge to the next generation of analysts and research scientists like you and me in industry as well as in academia. Dr. Venkat Manohar is currently the Director of Indian Institute of Chromatography and Mass Spectrometry, or as we call IICMS, and the President of Spinco R&D facility. Dr. Venkat has been practicing analytical science over a period of more than 45 years at various multinational companies like Piramal, Unilever, Searle India, etc., after obtaining a PhD in physics from the University of Madras. He has more than 70 publications and 7 patents to his credit. He has written more than 100 articles in Spinco's Cutting Edge, which is a scientific journal, over a period of a decade under the title of Sharing the Learning. Dr. Venkat Manohar is also a highly sought after and a distinguished speaker for various trending seminars from the industry, as well as a lot of these regulatory bodies as well. And recently, I think like around 2 weeks back, he was also the guest of, guest speaker at the CPHI conference, where he gave a talk on the very trending subject of nitrosamines. Before we start, I would like to go over the house rules. Please use the Q&A box only at any time to actually log in your questions. Dr. Venkat Manohar will answer them once the session is over. Today's webinar, which is the 4th in the 12-part series of the Sharing the Learning webinar series, will cover the various LC detectors. Without further ado, sir.
Okay, thank you, Janani, for your nice introduction. Good afternoon to all the participants. Today, I will first share the screen. Are you able to see the screen clearly?
Yes, sir.
Is it? Shall I go ahead now?
Yes, sir.
Okay. Good afternoon. A few minutes ago, when the participants are joining the seminar, our team were playing a small video on the use of light. Light is nothing but an electromagnetic radiation. That is how the place goes. And they also showed the picture of Albert Einstein, who found light can possess both wave as well as particle nature. Today, when we are going to discuss about the detectors of LC and beyond, the light plays very important role. As Janani has introduced me, I am basically a physics student. When you want to study the property of a chemical compound, the compound should undergo a physical change, not a chemical change. If the compound undergoes a chemical change, it will become a different compound. Therefore, when a compound undergoes a physical change, only the physical quality will change, but not that. As such, the identity of the compound will be retained. When we talk about the liquid chromatography detectors, we use the concept of physical properties of these chemical substances in order to detect them through liquid chromatography. As you are aware, as you are using, we know that the liquid chromatography comprises of a pump which delivers a solvent or a mobile phase. You have a column which does the separation of the analyte. Once the analyte is separated, it passes through a cell called flow-through cell detector where it is getting detected. When you are going to detect the compound, the most important thing is, the whole purpose of the detection is to determine how much is the quantity of the sample is present in a mixture of analyte. When we want to determine quantitatively, the most important thing is we use light as a as the source which can able to use the property of the analyte. For example, when we want to detect the compound from a mixture of an analyte, the most important thing that we should know whether the compound is able to absorb the light or able to emit the light, or does it undergo any other physical change. For example, if the compound has to undergo a physical change, a simple physical change it can undergo is a change in the refractive index of a compound. Refractive index is a physical quantity. Absorbing a light, physical quantity. Emitting a light, physical quantity. Therefore, when we want make a detector for a liquid chromatography, we use the light as a source of detecting the chemical compounds or the mixture of compound present in a chromatographic mixture. Very good. Is that sufficient? I want to know, for example, my compound can be a paracetamol, a drug, and when you are having this kind of compound, it has some impurities. The impurities will be 0.1%, 0.2%. Is that sufficient? We have to look something beyond. What is that beyond? Does the so-called impurity is a known impurity or a known related substance, or if it is unknown substance? If that is the case, even if it is present at a concentration less than 0.5% or less than 0.1% or less than 0.01%, can I come to know what it is? Can I identify it? This is where the word beyond matters. So, in the liquid chromatography, the detector does two jobs. One, it helps you to quantitatively determine the content of all the substances present in a mixture of an analyte, and depending upon the nature of the detector that you use, it gives information to you about some identification of those analyte compound that are present in a mixture. Therefore, to begin with, if you want to know the quantity of the compound present in a mixture, To what extent I can determine the quantity analysis? Can I see 0.1%? Can I see 0.01%? Can I see 0.001%? Therefore, if you want to use a particular property of a light as a detector, and we should know when you design a detector what kind of qualities or characterization that you want attributes to the detectors. Therefore, if I look at this, then what we will do is we will attribute various characterization of detectors. Therefore, a HPLC detector needs to exhibit, first, it should possess high sensitivity. Not only that, whenever you record a chromatogram, the most important thing is the noise it can generate should be very, very small, a negligible baseline. What is the noise? Noise is a parameter, but there is no sample. The detector itself will generate some kind of signal that should be very, very small. It is just like a baseline, or it should be 0. Okay. Now, and also when I use a detector, can I use the detector from a nanogram to microgram level, or a picogram to microgram level, or I can go beyond that, which is called dynamic range, large dynamic range. This should possess. Further, the detector possesses a lot of properties. There is a light emission from a source. There is a change in the refractive index. There is a mobile phase. There is a solvent and lot of parameters. There is a temperature, mobile phase composition. All these parameters are there. The detector, the analyte, or the analysis, or the quantification that you are going to do using a detector should be independent of these parameters. Okay. Now, you should have, when you inject the sample, entire sample should go inside the detector and able to detect. Everything should be detected, not partially. Most important thing, if I do analysis today morning, if I do analysis in the evening, if I do the analysis tomorrow, day after tomorrow, maybe after 6 months, I should be able to get same result of the same sample. Stability, which is over long period of operation. Detector should be stable for the entire time of operation. Even the reproducibility should have. Therefore, these are some of the properties of the detectors that when you choose a detector for this purpose. Many commercial HPLC manufacturers have considered all these points and they have used all these parameters and they have come out with different kind of detectors for HPLC. Now, depending upon what kind of property that we are going to use, I can classify detector into 3 categories. The first category is solute property. The second category is bulk property. The third category is others. When you come to the solute property is absorption of the light, whether using a fixed wavelength or a variable wavelength, or you can use a photodiode array detector. Most of you are familiar with these detectors. There is another detector where the compound can undergo under an electrochemical reaction, thereby it may produce a charge or it may produce a current. You can use both the properties. Some of the compounds will absorb light and they emit light also. That is called fluorescence. So electrochemical property, UV absorption property, or a fluorescence property, you people have made using all these properties, they make detectors. They're called solute property. There's another property called bulk property. Bulk property involves detector based on the change in the refractive index or change in the conductivity of the material. Therefore, this is called universal detector. Using these two properties, you can measure the concentration of a sample or impurity present in a mixture of compounds. The third property is what we call it as, the property is called as others. In the others category, there are, you can use what is called evaporative light scattering as a detector. Here also you use light scattering. What do you evaporate? You evaporate the mobile phase, allow the light to fall on the particles, it undergo a scattering. The scattering, after scattering the light, scattering is nothing but multiple reflection is called scattering. When the light undergoes a scattering, there is no change in the energy of the light. We call it as Rayleigh scattering. Use that property, you can measure the concentration of the sample. The other detector is the most important detector people are looking for, the most sought after detector called mass spectrometer. We will cover that also. The other detector people use what is called even nuclear magnetic resonance or NMR can also be used as a detector for HPLC. Of this, we will see a few detectors today, see how it can help us to understand quantitatively the presence of a impure related substances present in a mixture or the purity of a compound. With this, we will go into the detectors one by one. With this brief introduction, we will go to one by one the detectors. For all these detectors, all of you know very well, we use, all of you might have studied in your college days, Beer-Lambert's law. This is the property that we use for this purpose. And this is a detector that we normally use. This is the optics of the detector, and this is the formula that many of you know. This is nothing but a multi-wavelength UV detector. Very, very simple. Very simple. Use a UV lamp, deuterium lamp. Use a curved mirror. When the UV light falls on this, use another curved mirror where there is no loss in intensity. Then you have a diffraction grating. The diffraction grating helps you to choose the wavelength of detection, and it comes here. The chosen wavelength light comes here. This is where this is a flow through cell. This is where the sample is entering from the column. Then the waste is taken out. When the sample comes here, you can see here the sample will remain for some time. The sample continuously flow, and when the sample continuously flow, the light falls on this. The amount of light absorbed here is directed by a photo cell, and by a photo cell, this is a quartz tube, and this is a sample compartment, and the concentration of sample is proportional to the absorbance, where K is the molar extinction coefficient, I is the cell path length, the famous Beer-Lambert's law. This is a simple, straightforward UV detector which you have been using for so many years. No problem. This formula you know very well. Log IT by IT, where I is the intensity of the light absorbed, I naught is the intensity of the light at zero when there is no sample. You take the logarithm of this, then you can measure. This is called the so-called Beer-Lambert's law, where the absorbance of the light is proportional to the concentration. Correct? Thereby, I can quantitatively determine how much is the sample is present in a mixture of compound. Good. But the small hitch is here. The absorbance of the light depending upon the concentration. But at the same time, it depends upon the molar extinction coefficient. This is nothing but at what lambda, at what wavelength of the light, it has got maximum absorbance. A compound, depending upon its chromophore, one may have absorbance 254 nanometer, another will have an absorbance at 320 nanometer, another will have absorbance 225 nanometer. If the absorbance at a different wavelength are different, then the calculation of the concentration with respect to absorbance may not be equal. You have to use a relative response factor parameter to normalize the absorbance value. Thereby, you calculate the right concentration. Otherwise, you will be misled. Sometimes, if you choose a wavelength, 270 nanometer, some of the impurities do not have absorbance at that wavelength, then you will be falsely identifying the compound is 100% pure, but the impurities are not detected. This is the limitation of the UV detector. You may think the compound is pure, but it will be impure. If that is the case, what shall we do? No problem. Can I detect my compound at all wavelengths? The HPLC manufacturers have come out a different kind of UV detector where that UV detector can see your compound at all wavelengths. That's what we call it as diode array detector. That you can simultaneously detect at all wavelengths. We call it as spectrochromatograph. It makes your compound more pure. Your main compound, API, for example, may have its lambda max at 254. The impurity will have lambda max at 320. When you have set 254 nanometer, your compound, your impurity may go undetected. But when you are using a diode array detector, because it sees the compound at all wavelengths, the impurity will also be detected. That is why it makes your compound of API or your compound of interest more pure. This is optics. I have a photodiode array detector. This is the holographic grating, eluent from the column. This is a flow-through cell. This is a lamp. You can see this. What does it do? We use a xenon or a deuterium lamp. Sample is exposed to all wavelength. The holographic grating that undergoes a dispersion. Use not a single photo cell, but use a photodiode array. How does it look like? You can see here. This is the grating. This is the photo. This is a flow-through cell. This is a lamp. Entrance slit. Entire light falls on this. You can see entire range is covered. If that is the case, how does it look like? What shall I do with this? You have got a very good advantage. The manufacturers HPLC, they not only incorporated a diode array detector, they also incorporated, because of the information technology, lot of software features. One such software feature they have incorporated is what is called intelligent peak convolution analysis technique. What does it do? when you are injecting a sample, your column does the separation. We know very well. If the column is not separating properly because of the similarity in the chromophore of your compound of interest along with the impurity, we call it as co-eluting peak. If there exists a co-eluting peak, can my detector differentiate it? The answer is yes. I will show you a small example. There are a lot of examples are there. Because of want of time, I show the latest example where the intelligent peak deconvolution analysis technique can give you that kind of data. It accurately extracts and quantifies a single component from a co-eluting or poorly resolved peaks. Not only that, this technique uses a mathematical formula, what is called multivariate curve resolution alternating least square technique is called MCR-ALS. Don't get bogged down by this big name. Very, very simple. I'll show you very near. How does this multivariate curve resolution alternating least square technique work? I will demonstrate to you now. This is a data. You can say three-dimensional plot. This is the wavelength. This is the retention time. This is the absorbance. So three-dimensional plot. Now, if you make a plot between wavelength and retention time, we call it as spectrochromatograph. What do you mean by that? For every peak, you get a complete UV spectra. For every peak also, you get a complete chromatogram. For example, I have a mixture of three compounds. When I have a mixture of three compounds, they are not well separated. The concentration is C1, C2, C3. Now, similarly, for all these three compounds, this is the UV spectrum where you can see lambda max for S1 is different from S3, is different from S2. Therefore, spectral parameter where lambda max is different, the compound is not well resolved, but I want to know how much is the purity of the co-eluting peak. We will find out now. How does we do? It is very, very simple. Use this software. This is a measurement data. From this measurement data, what we will do is we take the spectrum, we take the concentration of the compound 1, this as a function of time, as a function of wavelength 2. Extract that. Similarly, you extract the compound 3 with its spectral data. Or similarly, you extract compound 2 with the spectral data S2. All are well separated through the software IPDPEA. The moment you separate them, then you can get the full information. I know what I am talking is abstract. That's what you think. I will show an example. I have taken three compounds: methyl acetophenone, ortho, methyl acetophenone meta, methyl acetophenone para. Ortho, para, meta, methyl acetophenone, three compounds. This has got a very good UV absorbance. But if you look at this chromatogram, I have taken deliberately ortho 100%, meta 100%. When I took the para ortho acetophenone, what happens is equal to, I have taken 1% concentration. That 1% concentration is buried somewhere. Only ortho and meta are separated. Para is lying somewhere here. You can see a small hump here. Literally, you don't see any hump at all, for example. Then what I did is, I used the software. I could be able to extract all the three peaks using the software. You can see this red color is 1% para methyl acetophenone. Now, when you see this one, I calculate a parameter called similarity factor. When I do a similarity extraction, my R square value is only 0.989184. Now, if you look at this data very clearly, I can show you that when it is the true value, when it is a decadulated value, the error bar is less than 3% for para-methyl acetophenone. You can see here very clearly the similarity factor in all cases 0.999. A compound para-methyl acetophenone where the concentration is only 1%, which was co-eluting along with the compound. Our separation was very bad, similarity factor was very bad, but I use a very powerful software. I'm able to extract the peak because I'm able to extract with the error bar of just 3.5%. My similarity factor is 0.9996, which tells you the purity of the concentration of the impurity they calculated is correct and within the error bar. This is the power of photodiode array detector with the features of deconvolution techniques where you can quantitatively estimate very clearly the compound. Impurity is present even though the separation is poor. Actually, the peak is lying in between ortho and meta. Para is lying somewhere here. Because of deconvolution technique, I could be able to mathematically separate them and calculate the percentage similarity factor, because of which I could be able to determine its concentration is only 26,000. You can ask me what is its true value in the table. It is very simple. I took ortho meta-acetophenone, only one compound, injected quantitatively, calculated its area. Similarly, 1% of para-methyl acetophenone, I calculated the area. Then similarly for the meta-para-acetophenone, I calculated, note down the area. Then after that you make a mix. When you inject the mix, para is not separated. Use a deconvolution technique and calculate the area because of deconvolution. All of them are very close. Error bar is almost nil, which very clearly tells you that even a co-eluting peak can be calculated using a deconvolution technique of the modern software. That is the modern PDE detector is very powerful for all kind of applications. You can determine the similarity factor. You can make your compound more pure. You can quantitatively determine the impurity present, though it is not separated. It's a very, very important information for all of you. Good. Everything is fine, sir. No problem. Provided the compound has got a chromophore. Sorry, sir. My compound is a fatty acid ester. Or it can be a polymer or a sugar moiety. What shall I do? Or it can be a inorganic ion. Can I use UV detector? No, you cannot use. I want to look for the trace level, the impurity, because it's a genotoxic impurity, for example. I want to know every trace level can determine the impurity. For that purpose, what you do is use the property of the detector, what we call it as fluorescence detector. When you use a fluorescence detector, it is very simple. The molecule absorbs the light and gets excited. When it gets excited, it emits the light while returning to the ground state at a higher wavelength. And this property is called fluorescence. And this is a flow-through cell. So you set this is a photo cell, you keep it here. This is a UV lamp. The advantage is selectivity is high, sensitivity is high, but the range of operation, the dynamic range is very narrow. Therefore, where you are looking for high sensitive detectors, if the compound is able to emit light, who is able to fluorescence, you can use this property and this detector as a specialized detector for high sensitivity quantitative estimation of special impurities that you may present in your compound. Okay, this is optics for that. This is a grating and this is a beam splitter, spherical mirror. All those things, same kind of optics that you can follow here. A typical example I can show you: naphthalene, acetophenone, 15 compounds, well separated. All of them are in the total analysis time is only 1800 seconds. I use a modern column. Okay, not in terms of minutes. How many minutes? Not more than around 20-25 minutes, not more than that. With 1800 seconds, you can able to separate and all of the fluorescent intensity and dibenzene, anthracene, all these things, compounds can be well separated. Okay. Sorry, sir, my compound doesn't have fluorescence. The compound doesn't have chromophore. It doesn't possess any property where it can use light as a parameter to get detected. Don't worry. We have another detector. This is called refractive index detector. What do you do is use a prism. The light undergoes the refraction. When light enters, light undergoes bending. This property you use in order to measure the concentration of the sample. This is a typical optical system for a refractive index. We can determine glucose, sucrose, maltose, lactose, xylose, and so on. This is a typical chromatogram from a RI detector. Okay, sir, but I want to detect the trace level. Can I use RI detector? No, the answer is no. Another thing, in the case of an RI detector, the most important thing is when you use a mobile phase contains solvents, acetonitride, water, formic acid, buffer solution, potassium dihydrogen phosphate, or sodium acetate buffer. So many things are there. The moment the mobile phase undergoes a change, if you use a gradient elution, the refractive index also undergoes a change. Therefore, not only for isocratic analysis, you can use the RI detector, but you cannot use for gradient elution. Sir, I am not able to get such a kind of separation. When I use the isocratic elution, I have to follow gradient. Can I use RI detector? The answer is no. What shall I do now? Don't worry. I have another detector. This detector is called evaporative light scattering detector. I use the principle of scattering a light. Scattering means what? Scattering by particles. What kind of particles? Particles that are floating in the air, small particles. When a light falls, light undergoes a multiple reflection. All this light intensity pick it up and arrange that and make them get back the light from the scattering principle and take that light and then use that as a property. This is where what I should do. Very simple. You have a nebulizer gas. This is my light source. This is my elution from the column comes in. When the liquid is coming, use a gas, produce particles, droplets. This concept we are going to use for some other purpose also. Remember this. I use a gas here. This is where the liquid is coming from here. I use a gas. From the flowing liquid, convert into droplets. The moment it becomes a droplets, then when it comes very close here, use a heated little bit. All this mobile phase will get evaporated. When the mobile phase is getting evaporated, what you get here is nothing but floating particles. In the floating particles, light undergoes scattering. You measure the scattering light. That's what you do. From the scattering light, I can determine the concentration. Since the analysis is independent of the presence of mobile phase, you are able to use a gradient mobile phase in this kind of product. That is why this detector is very famous. It is very famous for using many of the applications, even for protein analysis and things like that. This is a typical light scattering detector. This is how your assisting gas comes here. This is the photomultiplier. This is a source of light. These two assisting gases, they produce what is called the droplets. When they produce the droplets, they are uniformly traveling here. Now, when the light falls, undergoes scattering, there is a photomultiplier here. Now, this is how the actual picture where nebulizer gas enters. This is a mobile phase. This is a glass cell. This is a draining. This is the draining outlet. Now, what you do is you produce this bunch of droplets. These droplets will tell you quantitative of droplets you can produce. From this, you can calculate how much is the concentration. This is also called a universal detector for our kind of applications. Very good. Fantastic. We cannot allow you go home without detecting the compound. So you can use evaporating light scatter. You can use a RI detector. You can also use a fluorescence property. You can use a photodiode or a detector. You can use also the UV detector, and any of the one of these detectors will able to help you to analyze your compound. So our compounds continuously be analyzed. Example, you can see here, I have a glucose, maltose, maltose, etc. Where I use a helic column, all the compounds have been well separated. Oligosaccharides and maltodextrin mixtures, all of them can be separated by evaporative scattering, very clean baseline. Good. There's another detector. It uses a principle of aerosol detection. It is called corona charge aerosol detection. What does it do? How does it work? Very simple. The column element is first nebulized with a nitrogen or a air carrier gas to form droplets. Once it forms a droplets, they are dried to remove the mobile phase, producing analyte particles. When I produce analyte particles, these analyte particles meet another stream of nitrogen where it is positively charged with a high voltage, and that high voltage through a platinum corona wire. Such a charge aerosol is able to detect your compound very quickly, and the charge transfer occurs diffusionally to the opposing stream of analyte and is further transferred to a collector. How to visualize this kind of detector? This can be visualized through this picture. This is a gas inlet. This is the HPLC column. The mobile phase enters, your sample is coming here. This is a nebulizer or an impactor. Here, large droplets will go off to a waste. You produce a small droplet, the drying tube. Each drying tube, my solvent is slowly evaporating. They all come here. The droplets are coming here. At this point in time, I have a secondary gas stream coming through this path, and which is getting charged. The charge is transferred to the droplet. When the charge is transferred to the charged droplets will come here through this ion trap path, and it will enter here from the collector. I have an electrometer where it is getting totally detected. The process. By this is also another universal detector where you can determine the compound very accurately. Normally, this kind of detector we use occasionally, not quite often. This is very useful for inorganics. For example, if you look at this graph, I have got anions, I have got cations, I have got anions. The chlorate, nitrate, chlorine, phosphate, and then lithium, sodium, potassium, sulfate ion, and so on. Both anion and cation can simultaneously be detected by this kind of detectors. Otherwise, you have to separate anion exchange column. You have to separate cation exchange column. You don't need both. Both can be simultaneously detected by this technique. This is the advantage. Therefore, inorganic compounds can be analyzed. Organic compounds can be analyzed. Chromophore compound can be quantitatively estimated. Non-chromophore compounds can be estimated. Everything, by depending upon your requirement, you use the right choice of the detector you make. You can quantitatively estimate your compound present in a mixture of compounds. Nothing goes undetected. Clear? Very good. So far, I have been discussing only about detector, which has been doing only quantitatively, estimately the quantity of API present or purity of your compound or the concentration of the impurities. One question left unanswered. Can I simultaneously identify it? This is where your mass spectrometer comes into the picture. That is, you have to couple liquid chromatography with a mass spectrometer. What is a mass spectrometer? Most of you may be using mass spectrometer. Some of you have a mass spectrometer. Some of you have read about the mass spectrometer. Mass spectrometer is a very, very simple device. It contains only 3 parts. One is called source. Second one is called analyzer. Third part is called detector. All these 3 items, that is source, analyzer, and detector, they are all kept in a high vacuum unit. When I say high vacuum, how much is the vacuum? The vacuum should be of the order of 10 power minus 6 star. We use a turbomolecular pump. We use a rotary pump, high vacuum rotary pump, high speed turbomolecular pump, or sometimes we use a diffusion pump. And these 2 kind of pumps, they generate high vacuum, and your source, analyzer, and detector are all housed in a high vacuum unit, and such an entire this device is what is called mass spectrometer. What is mass spectrometer? Before we answer this question, a mass spectrometer needs a sample. Where does the sample come from? From a gas chromatography or from a liquid chromatography. Since we are discussing detector for HPLC, the source for the sample here is liquid chromatography. Therefore, we have to connect liquid chromatography with the mass spectrometer. Very good. Very simple, straightforward. We are able to understand it very clearly. Connect a liquid chromatograph to the mass spectrometer. Mass spectrometer, you have a source, analyzer, as well as a detector. They are kept under high vacuum. Very good. Now, in a liquid chromatographic system, I use liquid as a mobile phase, which is coming at some flow rate, say 1 ml per minute, 2 ml per minute, and so on. In the case of a mass spectrometer, I told you it has to be under high vacuum. High vacuum means no air. When even air is not allowed, how you allow a liquid go inside? Two contradictory things. One uses a liquid to separate your mixture of compounds and carry your sample into the mass spectrometer. A mass spectrometer can work if there is no liquid at all. Two contradictory things. We have a problem now. Don't worry. The manufacturers have done a wonderful job. What they have done is have a liquid chromatograph, have a mass spectrometer, connect both, not directly, but through an interface. Okay, I will do that. What is interface? What is the criteria for the interface? Very simple. Mobile phase should be removed. My sample only go into the mass spectrometer. If the sample goes in the form of a solid, again high vacuum, the vacuum will suck it off. Therefore, I cannot use my sample in the form of a solid or in the form of a liquid, but I have to convert my sample in the form of a gas. Therefore, the interface should be able to evaporate your sample. If it is a solid, convert into a gas. If a sample is a liquid, convert into a gas. First job. Second job, remove the mobile phase. The moment I completely remove the knock off the mobile phase, what happens? I automatically enrich my sample concentration. The moment my sample concentration enrich, convert the liquid or a solid into a gas. If you do these two jobs through an interface, the sample will enter into a mass spectrometer. There is no problem. How to do that? That's what we will see now. When we do that kind of ionization, that means what? I have to, then what happens? The sample goes in the form of a gaseous state. I have an ionization technique. I am an analyzer. I have also got what is called the detector. All these things are there. Now, before that, I have to use an interface. In the case of a liquid chromatography technique, most of you heard the word what is called electron spray ionization technique. You might also heard about the word atmospheric pressure chemical ionization technique. Please remember that. I have not yet defined to you what is mass spectrometer. I have only shown you a mass spectrometer consists of an ionization, an ionizer, analyzer, detector, nothing else. The electron ionization, chemical ionization, we use the gas chromatography technique. I will not discuss about that. Only for sake of understanding mass spectrometer, I use it. Okay. This is called electron ionization. I have a molecule, Ma. I do ionization. The molecule gets ionized. When I say ionized, molecule becomes neutral molecule. I remove the electron, it becomes positively charged. Any charge a molecule possesses, it becomes an ion. All happens in the gaseous state. This molecular ion further undergoes a disintegration. You produce a fragmented ion. You also produce a neutral fragment. When you do both, immediately you get the complete molecules intact. Here, this is called, I use an electron beam here. When I use electron beam here, it undergoes electron ionization. It is called, ionization efficiency is very high. It has got highest sensitivity. The mass spectrum that you get is the fingerprint of your compound. Beautiful. Sir, I have understood nothing. What is this? Totally confusion. I don't like equation. I am a chemist. Don't worry. Remove the equation. This is an example which I have known for the last 35 years. I want to find out another example I am not able to do. So I will share with the same example to define you what is mass spectrometer. This is a glass tumbler. Take a stone, hit it. Being a glass tumbler, the tumbler breaks into pieces. You get a lot of pieces. One more piece. Oh, one more. One more. Anything else? No. Okay. Now, if you are a little bit patient person, sit, assemble, get the glass bottle, tumbler back. You have got the glass, you are assembled all the pieces, pasted it, you got the tumbler back. That is a mass spectrometer. The glass tumbler is nothing but your compound. The stone is nothing but beam of electrons. If the beam of electron bombards the molecules are fragmented into ions as your tumbler breaks into pieces. The fragmentation pattern that you get is nothing but, if you know how to read the fragmentation pattern, you get back your molecule as you get back your tumbler. If a beam of electron bombards the molecules are fragmented into ions. The fragmentation pattern that you get is the characteristic of your compound, which if you know how to read that one, you get back as you get back the tumbler, you get back the compound. Now you see this equation. This is my molecule. I bombard with the electron. The molecule are fragmented into ions. The fragmentation pattern that I get is the corresponding to the mass spectrum of my compound. Okay. This is how the sample comes. I produce the vapors. These are gaseous ions are coming. How do I produce the beam of electrons? Very, very simple. Have a filament, a tungsten wire, heat it to very high temperature so that it starts emitting the electrons. Now you produce electron beam here. When this electron gas, then this electron gas meets this beam of, when this compound meets electron, when the compound meets the electron, the high energy electrons, what happens? The electron beam, immediately what happens? Your compound is getting ionized, you produce the positive ions. The positive ion that you produce, use focusing lens, produce the ion beam. That's all ion source. Now, if you look at this, there are several methods you can produce ionization. Electron ionization I have shown you. You can do chemical ionization. You can do field ionization. You can do the field dissolved ionization. fast atom bombardment ionization, electron spray ionization, atmospheric pressure chemical ionization, matrix assisted laser distortion ionization called MALDI technique. Using any one of the techniques, we can produce the ion. Now, in the case of a liquid chromatography, we use normally we use mostly electron spray ionization or atmospheric pressure chemical ionization. I will focus on only these two. Before that, we should know how to interface liquid chromatography with MS. You want to know how to do it? You are doing in your house. How? You see here. This is how you can throw water, mobile phase, flow from liquid column. What you do is, do a simple job, convert into droplets, gardening, you see, convert to mist in ionization source, convert flow of liquid from LC column to a mist in order for ionization to occur. That's all. Very simple. How to produce a mist? Use a nebulizer, like evaporative scattering technique. You already seen that picture. Therefore, this is how to convert a liquid column into a mist producing droplets. You want to see that picture? I will show you. You can see very carefully here. Nothing is there. This is the ion. This is nothing but electron spray ionization source of inside a liquid chromatographic MS mass spectrometer. If you see here, this is spray mist coming up. In the case of here, when the liquid is flowing, when the mobile waste flowing from the liquid chromatogram, from the chromatograph liquid LC to MS, this is the spray. This is the formation of mobile phase waste upon optimization of nebulizer spray in our, as observed in our mass spectrometer 8040, 8045, 8050, and so on. Very nice. What is electron spray ionization? How does it work? What is all this production? What is the ionization process? What is desolvation? All those things. How does the electron source looks like? We call it as APCI or atmospheric ionization. How does it work? All these details we will see in the next seminar. To summarize, I have discussed with you UV and PDA detector, fluorescence, RI detector, ELSD, CAD. I have introduced today mass spectrometer. The coming 4 to 5 lectures, next few months, is going to be highly excited for all of you, and you will all enjoy the coming presentations very well with more participants. And I thank you all for your attention.
Thank you, sir, for the highly incisive talk on LC detectors. In fact, I was personally curious about the identification and the determination of purity, especially in the co-eluting peaks using the IPDA software and the PDA detector. And also, as as all the chromatographers know, the impossibility in applying gradient elution in RI, for which you have explained that the evaporative light scattering detector takes care of that particular limitation.
Yes.
And also how to interface the LC with the MS, and a very brief overview of the ionization technique. And I think like on the whole, it was a highly insightful webinar. We will now be sharing 3 poll questions to all our participants, after which we will start our Q&A session. Yes. Can we have the poll questions, please?
Yes. The photodiode detector can be used to quantitatively estimate.
A, the purity of the main compound, or the or the impurity profile, the co-eluting peak, or none?
So purity main compound, all detectors will do. Impurity also we can do. The photo detector gives you co-eluting peak very clearly, as I have shown you an example. So that is the answer.
Yes, so we haven't ended the poll yet. So should we end it right now? Yeah. So as the results say, the co-eluting peak is actually the correct answer for this.
Thank
So
you.
we will next go on for the next poll question. If that can be flashed right now, please. So the sensitivity of a fluorescence detector in HPLC is A, very high, B, selective and very high, C, same as the UV detector, and D, normal. So which of this is it going to be? We will just share the answer with you once the poll has ended.
Thanks.
Yes, can we end the poll right now? So it's so selective and very high is the right answer. And sir, your comments?
Very good. So I think my lecture is delivering its job.
Yeah.
Very good. Very good. Well done.
So the next question, yes. Can we have the last poll question, please? Yes. So mass spectrometer can be used as A, a very high sensitive detector, B, qualitative detector, C, qualitative and quantitative detector, and D, detector to record MS spectrum. Please log in the most appropriate answer for this question. Yes, can we end the poll now?
Good. Very good. Very good.
The qualitative and quantitative detector, if you actually know, the MS is, it can be a very high sensitive detector. It can be a qualitative detector and a quantitative detector. It can also be used to record an MS spectrum. But the most, appropriate answer would be, it is a qualitative as well as a quantitative detector. And sir, your comments on this, please.
Yeah. That's the right answer. Most of you have answered that, and probably what we will do is how it is doing that such a job. We will see in the coming days in our presentation.
Yes, sir. So now I will also be going. So I'll just start the Q&A session right now. We have a lot of questions, and I'll just start them one by one. Okay, so we have the first question from Saujanya. It says, sir, kindly explain on the difference between the refractive index detector and an evaporative light scattering detector.
The refractive index detector is used when both are universal detector, but refractive can be used only in the not with the gradient illusion system. We can use the isocratic system. Evaporative light detector can be used even with the gradient illusion system. That's the difference between the two.
And the second question, sir, does IPDA work if the co-eluting analyte is unknown? This question is from Mr. Tarun Goyal.
Yes, because if we take we do it using a complete UV spectrum, therefore even to work for the unknowns actually.
Okay. And again, we have one more question from the anonymous attendee. Will the IPDA work for finding out the co-eluting peaks of isomers?
Yes. That's why I showed you ortho para meta case I have demonstrated.
Okay, then we have one more question from Mr. Prabhu. I have a doubt on the anions or cations in the effluent to detect concentration using CAT detector. My actual doubt is how much concentration limit, higher or lower, of cations in the production effluent?
It can go down to nanogram level.
Okay. And sorry, sir, one second. Yeah. And then, okay, all detectors can be used. Okay, so so what Mr. Mangesh is asking is if all the detectors can be connected to the prominence I system for different compound analysis.
Yeah, it can be done. That can be done. Yeah.
And then we have one more question by Mr. Venkata, and he says, "Hi, sir, I have two questions. One, could you please explain the role of various mobile phase for different target analytes? Two, difference between positive and negative electron spray ionization."
So different mobile phases are needed for different type of targets because the polarity of the analyte and the polarity of the mobile base will determine the separation efficiency. If the mobile phase polarity is similar to that of a analyte, then that gives a better separation. The second question, difference between the positive ionization, we will wait till my third lecture comes. He has to wait for next couple of lectures.
Yes, sir. Then we have one more question. Can we use more than one detector with HPLC?
Yes, we can use that.
What detectors can be used together and how it will be helpful for scientists?
Okay. First, you have to connect a UV or PDA detector. From the output of PDA detector should go to a fluorescence detector. From the fluorescence, it can enter into a RI detector. From the RI detector, it can go into evaporated scattering detector. You can get 4 detectors at a time or 5 detectors.
Yeah. One second, we have one more question also from Mr. Venkata again. Okay, once again, oh, sorry. Yeah. Also, when we are able to quantify using detectors, what is the purpose of interfacing LC with MS?
A very good question. When we use detectors up to UV or a RI detector, everything, the sensitivity can be typically not more than 1 nanogram per ml. Whereas today, the requirement in the regulatory requirement for some of the genotoxic impurities is around 1 picogram per ml or less than that. In such situations, we have to go for LC coupled with MS.
Yeah, and we also have another question from Mr. Satish. Is the PDA detector as accurate as UV?
Yes, accurate.
Then one more from Mr. Tejas. Sir, what is the criteria for choosing ion source for unknown compound mixture? I
will explain when I do what is called how to do method development using MS system.
Okay. Can I have the last? Okay, fine. That is, we can attend it offline. And okay, explain which detector is most sensitive, UV or PDA, and why?
In this case, currently both are equally sensitive because both use the property of chromophore of the compound. Only difference in the case of a PDA detector and UV detector is the one is a multiple wavelength detector, another is a single wavelength detector. That's the only reason.
Okay. Then we have a question from Mr. Vikram. PDA and RI can be used together?
Yes, very much, very much.
Okay. Yes, sir. And then one more question. Okay, that is on PPT. And okay, why the RID response is very low compared to UV or PDA? Why is the RID response very low when compared to UV or PDA? This is a question from Mr. Nishant.
When I use, in the case of a refractive index detector, we are not measuring absolute refractive index. We are measuring the relative refractive index or refractive index difference. The difference in refractive index is very, very small for a given compound. That is why the response is very low.
Okay. And Mr. Mridul is asking, what is the major difference between the UV detector and the PDA detector?
The one major difference is UV detector at a given time, you can select only 1 or 2 wavelengths, whereas PDA detector, you can select all the wavelengths.
Oh. And this is a question from Mr. Bharat. How can we find the impurity present in an API which is having a different lambda max from API and eluting at a different RP from API apart from LCMS?
Use PDA detector.
Because that has the entire spectrum, of the wavelengths. Okay, the next one is
I answered.
that I think we've already answered. And okay, then we have one more question. Oh yeah, a few more. Hello, sir. We are having aflatoxin analysis for which fluorescence detector is the only thing we can use. Okay, can we do aflatoxin using UV detector?
Yeah. You have to use fluorescence detector because sensitivity is very high.
Okay. And one last question from Mr. Bharat Reddy. So my compound is suitable for both GCMS and LCMS. Which one is good for my first choice? But I think that's...
In your case, I prefer LCMS because I need not... Suppose the compound contains some mixtures which undergo thermal decomposition high temperature, GCMS is not useful. Therefore, I prefer to have LCMS. Okay.
So I think that will be all, folks, because I think we have answered almost all the questions. And if you, for more information on the technologies that has been discussed today and how it can help you, in your organization with your scientific pursuits, please contact us. And I would just ask one of my teammates to actually paste the link here. And if you have any more questions, please write to us at sharingthelearning@spincotech.com. And we will get back to you with the answers as soon as possible. And thank you very much for being here with us today and attending the 4th session of Sharing the Learning webinar. And next, as Sir mentioned, the coming sessions will focus primarily on MS, both, on the basics and on the qualitative as well as on the quantitative analysis aspects. So thank you once again for joining us. And we will see you next month. Thank you. So I'll now be closing the seminar. Yeah, and thank you everyone for joining us.